Another lecture in our series. And tonight I'm very happy to welcome Jan Knippers. Jan, well, he has this funny combination. He studied all the way in the north in Berlin, where he also did his PhD in 1992. And then he ended up in what is by and by, I suppose, sort of a technical, engineering-wise haven or hotspot in Germany, namely the whole area around Stuttgart. He went to work for Schleich und Bergemann, a very prominent German engineering firm, after he finished his PhD. And then in 2000 he was called to be a professor in Stuttgart and took over the institute that he's now leading, Institute for Structural Design. And and then also important milestone was, of course, then a year later in 2001, forming Knippers and Helbig, Advanced Engineering. It's a firm that has grown over the years, and today it has offices both in Stuttgart as well as New York. And this sort of spread also, I think, is telling of Jan's own development. To look at the list of research projects that they do in Stuttgart is extremely impressive. We first met quite a few years ago when I had the opportunity to visit the institute and speak about my own interests in fiber-reinforced composites at the time. I imagine that we were, I don't know, mutually shocked. My coming from one of a background with these materials that was full of ideas and visions, to put it that way, and Jan's being an extremely down-to-earth and practically oriented approach. But I think this one can also see in the development of Jan and colleagues' research and work. They have proceeded to do unbelievably impressive research projects, but first and foremost being able to apply these on a building scale, if not always, and on and off on a building scale. And that, I believe, is fairly rare. It means also that the research is, that efforts with respect to precisely this research on fiber-reinforced composites, which is only one part of the research they undertake, is pushed in an extremely valuable direction, where, because it's been, in very many cases, very important work and investigations going on both with these materials and in other realms of structural design. But to see that then by and by applied to a building scale is, I believe, a very important development. This is also true for his own interests in biomimetics or biomics. So in the last 3 summers, in collaboration with ICD, the neighboring Institute of Computational Design, led by Achim Menges, there's been further efforts, both in terms of material design on wood, basically on computational strategies, but not the least in terms of also how bionics or references to nature and biology may drive, models from that may drive the design process. Jan, we're very happy to have you here tonight. We look forward to hearing you.
So thank you, Johan, for inviting me and for introducing me. And thank you all for spending this wonderful evening here with me in this dark room instead of sitting outside at the banks of the river. So, as Johan said, I'm a structural engineer, and my interest is the development of new efficient structural forms for architecture. So how do we come to new performance-oriented structural systems? That's my personal interest. I want to discuss this point with you this evening. To do so, I first want to explain how we use computational tools today in the practice of building construction and building design. So which level, which status did we achieve in the application of computational design tools in architecture? To explain this, to discuss this, I would like to show you this project that we were working on during the last years, together with Massimiliano Fuxas, who is well known here in Frankfurt from his Teilgalerie. And he won the competition for the Shenzhen airport in the south of China, 2006. We were his engineers, and this was his winning competition entry, a rendering for the competition. And you can see this is a very large building, 1,400 meters long. And his initial idea was to have this kind of perforated building skins, 2 layers of cladding in between the structure, and this skin is perforated, so you have different light situations within the building. So this was one of the early models built in our office, showing the idea. It's a very, very large building, 1,400 meters long. There are certain areas where you want no light. There are other areas where you want a lot of light. And the idea was to adjust these openings in the cladding according to the local requirements in this very large building. That was a basic idea for the facade of this terminal. So we had this basic modules here with 2 design parameters: the size of the glass and the slope of the glass, inclination of the glass. These were the 2 design parameters, and we adjusted them to the various conditions of building physics, daylight, and the visual connections that you wanted to have from the inside to the outside. So what we basically did is we set up a range of modules, and we allocated them to the terminal building. This is an Excel sheet representing the concourse of the building, and each color stands for one module type. And we printed these Excel sheets and sent them as a printout to the Fuxas office, and he took his pencil and marked how he wanted to have the building components, the components of the facade on the concourse building. So the structure itself is quite simple. It's a framed truss, very simple structural system, but the geometry is very complicated. On the left side, you see a rendering from the competition phase, showing this concept of a stretched metal sheet mapped on a single curved surface. But unfortunately, the surface is double curved, and it's very complicated to map this pattern on a double curved surface, because it's not developable. So we needed some refinements, adjustments to allow for application of this pattern on a double curved surface. It's also very interesting that even though we are quite trained in using all these computational tools, we needed absolutely crucial to have this kind of small physical models, because otherwise the whole geometry is too complex to understand. So from the very beginning, we were working with these physical models. And this was a process of stepwise refinement and modification, adjustment of this 3D model to fulfill all the requirements to avoid any discontinuities or to achieve planar glass panes. That was very interesting because it took us, 12 to 18 months to develop this parametric model, including all the structural members as well. So it took us, 12 to 18 months to develop this data model. But during that time, you don't have anything to show or to hand over to the client. So you always go there, you say you work on the model, but you have nothing to hand over. And that is a quite difficult situation to keep the client calm and to avoid any nervosity of him. So this is just based on Excel and Rhino, so it's not any kind of rocket science computer program $1,000 million software. It's a very simple, basic computational tools that are used here to define this geometric model of the terminal building. What I think is very interesting and what is, as far as I know, not really recognized so far is that this kind of working on a 3D digital model is really a different design process from what we usually have in building construction or in architecture. So usually when we design a building, usually it's the way it's up there. That first there's a concept, architectural concept, geometry from the architect. Then the data is handed over to the engineers. They work on all the technical functionalities. And finally, we hand over our construction drawings to the constructor, and he fabricates all the elements and puts them together on site. But this process, as we had it in Shenzhen and also for other projects, is very different because there's one data model and everyone is contributing to it in some way. Yeah? But who is doing what and who is responsible for what is not defined by any regulations and has to be discussed and agreed each time again. So in this case, we were, as engineers, responsible for the 3D model, for the basic 3D model. In other cases, special geometry experts are involved, but I think it's a very important factor that you, as part of the design team, define and discuss your own role and your own contribution to the project. That's also this breaking up of role models is, I think, also a very important aspect for innovation in this kind of process. So here, Massimiliano on the side, a few words about the construction sequence. You can see in the back, you can see this movable scaffolding supporting these spheres, and then the spheres are, then the members are welded to the spheres. Yeah. So while steel construction, here my partner Torsten with Massimiliano on the side. The construction before the internal cladding was installed during installation. And this is an image photograph taken 2 or 3 months ago. The terminal building will be open to the public in summer this year. And you can see how the light situation is varying. You can see that in some areas it's closed surface. In other areas, a lot of daylight comes in, and you can see the structural system behind the internal cladding. You cannot talk about, this is the entrance hall to the concourse building. So you cannot talk about construction in China without talking about construction speed. Yeah? It's a story that has been told many times, but it's still very fascinating, especially when you have this background that you in Stuttgart or Berlin airport. So this is, the competition was 2006, 2007, winter 2006, 2007. Year 2010, the foundation works was completed already. 1 year later, all the steel construction was completed, and another year later, the whole steel works were completed, and this year now the terminal building will be open to public. I think that this project reflects quite well how computational tools are used today in architecture. Yeah? They're used to design complex geometries, complex facades, but I have to say, as a structural engineer, the underlying structural system is quite conventional. Yeah? It's a two-hinged truss arch system, a little bit fancy, the geometry is a little bit fancy, but the basic structural principle is very well known and very traditional. And I think that is very typical for the application of digital design. We're always talking about complex geometries, but we never talk about, or very rarely talk about, how to use computational tools to improve the performance of the structures. Yeah? And that is a point where I want to work on in Stuttgart at the university. And I think that comes from its origin in the fact that architects and engineers think very differently. Yeah? So architects and architecture basically always seeks for a very individual, unique solution representing the specific conditions of site and function. And Massimiliano is, I think, a particularly good example for that. So he's always looking for a very special appearance of his buildings. Engineers think exactly the other way around. Yeah? To achieve integrity of the system, to achieve functionality of the technical system, engineers always tend to use the same typologies that are approved and evaluated again and again. Yeah? And that is why we have so many problems, I think, in communication between engineers and architects. That is a very completely different way of approaching the design task. Yeah? Engineers look for the typology that fits to the project, while architects look for the unique expression. And to explain this a little bit, I want to always show this image because for engineers, the turning point, important turning point in the development of our profession was the invention of structural calculation, of statics. Yeah? You can see here that statics were, mechanics as a science go back to Galilei, to Renaissance, but structural calculation as a design tool, that is something that was invented in the second half of the 19th century. Yeah? And you can see here what happened. The lower bridge here is a bridge that was built before we had statics, yeah? And the large bridge was built after the invention of structural calculation. And you see two major differences. First one, enormous increase in performance and span. Yeah? Suddenly, span is possible that was not thinkable before. But secondly, before it was a quite wild arrangement of vertical, horizontal, diagonal members according to some kind of experience made with other bridges. But then you had this clear typology of the two hinged arches. Yeah? The two hinges there are not to increase the efficiency of the system. The two hinges are there to make it calculable, to allow for a reliable calculation of forces and deformations. And you can see that everywhere. You can see it also for these large halls. Suddenly enormous spans, but the same typologies are used again and again. I found this book showing all the railway stations built around the turning from the 19th to 20th century, and they all use the same identical structural system. Yeah? 2-hinge arch, 3-hinge arch. And this thinking in models and typologies, that is something that governs engineering till today. Yeah? You can see here, even in times when we have computer programs, we can calculate everything, we still use the same typologies. And also, this is a cross-section of the Shenzhen airport. I'm not better than my colleagues. We also use maybe crazy geometries, but the structural system is basically the same that was invented in the 19th century. And the question now is, how can we invent, find new structural systems beyond this typologies? And this system here is something that is, in terms of the 19th century theory, impossible, because it does not have 2 hinges or 3 hinges. It has 1, 2, 3, 4, 5, 6, 7 hinges. So it's not stable. It's an unstable system in the classic theory of structural mechanics. And this is only possible by geometric variation of the geometry. So it's not longer a linear arrangement of identical arches. It's a complex arrangements of geometrically differentiated forms. So the hinges are the weak points of the arch, and to achieve integrity, you have to vary the position of the hinges in the arches. So this up and down of the waves is something that comes from a structural need and is not based on an artistic, aesthetic intention. So this is an example for a structural system, a new structural system beyond typologies, which is possible through computational fabrication and design. Yeah? But usually, and this is also not only the geometry, but also the fact that usually engineers try to avoid deformation, deflections. Here we need deformation to achieve integrity. Yeah? You can see that the lamella is so fragile, so weak, so 1, 2, 3, 4 students have to carry them, and integrity is achieved only by bending and connecting them to the neighboring strips. So my experience is that schools of architecture always talk about computational design and computational fabrication, but what is not recognized is that we also need the aspects of computational mechanics as the third element to design new forms. Yeah? Only since 10 years, I would say, we have the computational tools available to simulate large deformation and anisotropic material behavior. So this aspect is also very important for new structural forms. So this system here is based on the individual creativity of our students and our PhD students, but what could be a consistent strategy to achieve a new structural systems, yeah, beyond typologies, which is not based on a genius. Yeah? And the strategy that we propose and we follow is not very new and not very original. Others looked in that direction before. It's to look at systems which are not governed by the criterion, by the paradigm of calculability, but which are developed by self-organization to fulfill multifunctional requirements. So we try to understand biological role models to look for new performance-oriented systems. Yeah? And this is what we try to do now. And that leads to the point that, well, that's interesting because the way that we as engineers or architects design our systems, no matter if it's a house or a car, could not be more different from the way natural systems are designed. Yeah? And this comparison is interesting. So what we have here, we have for every functional requirement, we have one component. Yeah? So, and this first result of that is that these systems all have a very limited redundancy. So one of these 4 wheels is flat, the car won't go. Yeah? So it's limited redundancy. The second aspect is that if each of these components is optimized to fulfill one or a very limited number of requirements, this leads to a huge amount of different materials. So the tires are optimized for maximum grip, minimum wearing. That leads to a specific rubber. The dampers are optimized for maximum energy absorption. That leads to a specific metal alloy. So we have a huge variety of different materials used for this technical system. And at the end, all these very different components are put together to form the system. And then we have the cover of the car, the body of the car, which forms the outer form of the car. And this could not be more different from the way that structures are designed in nature. Yeah, you can see here that this is only one material. These are all cellulose fibers. So it's organic molecules, but with locally highly differentiated physical properties and chemical properties. So some of them are stronger, they take the loads. Others are there to transport water from the roots to the leaves. Others are there to recognize chemical signals and so on. But it's only one material, one consistent material with differentiated properties. And this is also an example that is has been shown thousands of times, but it still is, for me as an engineer, absolutely fascinating. That's this deep sea sponge. It's a sponge like this size, 20 centimeters, made of a very brittle glass-like material. And on the macroscopic level, it looks like a steel tube with diagonal stiffening members, as we as engineers would design it for a high-rise building. But when you go deeper into it and see how it is constructed and how it is made, you always see that one component is made of many components, which again are made of many components and again of many layers, all with the same material. The way it is constructed and made is completely different from any technical system. So, and you find this principle of hierarchical structuring that's omnipresent in nature, but nowhere used in technology. So we have these design principles. You can describe them and define them, but basically they're all the same. They're all using one material from here to here, or from one material from here to here, but with locally differentiated properties. And this is well known since many years, but now we are at the point where we might have a small chance to transform these principles into building systems. Yeah, and that's what we try to do, what we try to investigate and analyze together with students. So our first project was the sea urchin that we did in summer 2011. And it's a modular shell. It's a challenge that we face very often also in building construction. Think of shells made of precast concrete elements or of glass. This is also a modular shell, and we try to understand the underlying structural principles, to analyze it and to transform it to an architectural form. You can see how these plates are connected of the sea urchin. They have a specific finger joint arrangement, which has a high capacity for shear forces, yeah, and a high capacity for compression forces, but a low capacity for bending and for tension also. And we transferred this to this kind of finger joints here for timber plates. Yeah, and this is possible. I mean, this finger joint technology is well known in timber construction, but usually restricted to rectangular or planar situations, and by this robotic fabrication we can adjust it to any kind of geometry. And this specific load-bearing capacity of this joints here, this high shear strength, high compression strength, but no bending strength and no tension strength, this leads to the specific arrangement of this hexagonal plates, yeah? Because when 3 edges meet in one point, you can form a stable shell structure even though the capacity of the joints is limited. And again, it's not difficult here to do the structural calculation or to do the mechanical tests, but the point is, the question is, how can you include the structural behavior into this design chain? Yeah, that's the key point and the key question that is the main focus of our research. Yeah? So this was again done by Achim's group and by my group. And what is interesting here is that this really is a different kind of collaboration between engineers and architects as we usually do it, because these are all Achim. Everyone has to define his own role. And this is Elias from Achim's group. He's doing the control of the robot. It's a tough engineering job, I would say. And Ricardo and my group think about solutions, how to include the information from the structural design into the computational design process. So everyone has to define his own contribution, and this, what I said before, this breakup of these role models, traditional role models, that is, I think, very important for innovation. And it was not our intention to build a large sea urchin. Our intention was to show that this, or how this principle of the sea urchin could be applied to a free architectural form which is characterized by cutouts or by edges or by all kinds of irregularities. And you can see how these modules follow the mechanical loading, where you have high forces here, you have smaller and stretched modules, and where you have smaller and regular forces, you have these larger and regular hexagons. So we try to do this each year. Last year was quite tough. We investigated this Lobster, which is also absolutely fascinating structure because this is one material from here to here, the same material. These are these chitin fibers embedded in a protein matrix, and only also the eyes are also covered by this exoskeleton. And only by adjusting the arrangement of the fibers and the properties of the matrix, very different mechanical properties are achieved, yeah? From extremely tough and hard to very flexible and elastic. Yeah? Only by differentiation of the fiber layout. Yeah? You can see here, these are tests that were done. This is the mechanical strength here in this clause, and this is the mechanical strength in this connecting membranes, so very different mechanical properties. And our students, we now set up a collaboration with biologists from the University of Tübingen, and we can do there together with them, we can do this analysis. You can see here the epidermis, that is the living body of the lobster here, cells. And here you can see the cuticula, the different layers of the chitin fibers. You can see them here. And the outer part, they have this mineral additives leading to this very hard exoskeleton. So we try to find an architectural structural expression for this concept of adjusted fiber layout as well as of geometry. You can see that this very strong claws, they have this specific stiffening rib leading to a very strong and hard element. Yeah, you can see here this is a representation of this geometry aspect, and the black fibers are the carbon fibers that take all the loads, and the white fibers are the glass fibers which form the envelope of the building, pavilion. This is a production sequence. We were also looking for a way of, we ask ourselves, what could be a reasonable production technology, fabrication technology for fiber composites in building industry. We know that especially in Stuttgart, they put a lot of research effort on lightweight structures for car industry, but car industry means thousands of identical pieces, and in building industry you have unique elements, and if you build a form for a house and then put fibers on it, you could build, I mean, that makes no sense. Yeah? You need different ways of fabricating them, and that's how we try to answer the question how we could build large elements and elements who are only produced in a small series or even as unique elements. So all the winding logic, different ways of winding. These are the carbon fibers, these are the glass fibers to form the space. All this, again, the structural analysis, we had 6 geometry parameters, diameter and height of this point, of this point, of this point. We varied them. These were the basic fiber layers, and we did structural analysis, tried to find out the optimum configuration, and then we did all the optimization of the fiber layers for the optimized geometric configuration of the pavilion. This was one of the first test runs. The fibers are still dry. That's why they are so shiny. You can see here, you cannot see it, but here is somewhere the roll where the fibers are, and then the robot places the fiber on this rotating scaffolding. Yeah. Next one is from the perspective of the robot. Black ones are carbon fibers. That's what this is what is used in aerospace industry or in Formula One racing cars. So the very stiff and strong fibers. The white fibers are glass fibers. They are used for surfboards, snowboards, sailboats. They are the soft and cheap ones. Yeah. So what I found interesting is that this is a fully automated process, but the surface is not at all perfect. Yeah? It shows how the thing is fabricated, and it also has a kind of three-dimensionality and depth that you can see here. Yeah? So this is the building as it was installed last year. Again, the stiff black ribs, and the soft white walls envelope. And for me, what is interesting here is that this is something that is really far beyond any typology in building construction. So there's not one path of loading, of load transfer. It's a complex arrangement of fibers, and you don't know exactly what happens here with the forces, but it's this kind of complex arrangement and multi-layered arrangement of fibers that leads to a stable system. Yeah, as a new expression of adjusting stiffness and load-bearing elements to a load-bearing structure. So what we could do now is you could extend this comparison to movable systems, movable structures. So when we as engineers design movable structures, we use either soft elements like cables or textiles with no bending stiffness, or we use rigid elements as steel girders with very high bending stiffness and connect them by bearings or joints. Yeah? That's how we do moving systems in building industry. And we have a motor somewhere here, an external actuator actuating all these systems. And again, this is very different from what nature is doing. Yeah? Nature is not using either stiff or soft elements. Here we have a locally adapted stiffness according to the functionality of the system, and we have an internal actuator. The whole thing is actuated by internal change of pressure in the cells of the element. Yeah? And we also investigated this. We had teamed up with biologists from Freiburg and had a look at this bird of paradise flower. And the special thing about this flower is that it's pollinated by a bird. A bird is very heavy compared to a bee or another insect. Yeah? And that's why this petal has this porch, a stiff, quite stiff porch. And when the bird sits down, the porch bends down, and the pollen that was protected before by this blue leaves is then exposed and can be lifted by the bird to the next petal. You can see it here. This is a bird of paradise flower. The load is represented by this force here. The pollen is protected, it bends down, and then the pollen is exposed and can be lifted to the next, can be transported to the next petal. So it's a very simple system, and we investigated, analyzed it. What we received from the biologists is this very complex section of the petal, which looks, for us as engineers, extremely complicated, thousands of fibers and pollens, and no one knows what they are good for. But by stepwise abstraction, by stepwise cutting off all elements that are not needed, you end up with a very simple mechanism that you can see here, a stiff backbone and a soft leaf. And when you bend the stiff backbone, this leads to the sideways flapping of this leaf. I hope that you can imagine how this works. Yeah? It's a very simple mechanism. And of course, you could ask me as an engineer, why do we need this inspiration from the bird of paradise flower to end up with such a simple mechanism? And the answer to this question is that for us as engineers, this is something that we consider as a torsional buckling failure mode. Yeah? So for us as engineers, this is usually a failure mode, and we were trained to avoid this kind of failure by complicated analysis or stiffening mechanisms. And nature uses it as a method to actuate a complex movement by a small actuation. Yeah? By small bending leads to a complex and large deformation. And that is what nature does and what engineers usually do not like. But this change of perspective, that is something that is coming out of this biomimetic inspiration. Yeah? And we transform this to mechanical models, to finite element simulations. We build prototypes with the friends from ITKE, Denkendorf, where we also met once. And these are elements which are only made of fiber-reinforced polymers. You can see here additional fibers. You can see how here is one glass fiber mat, two fiber mats, and this is only deformed by bending of the backbone. Yeah? And this was a project that was widely recognized, won a couple of prizes, awards, not because it's the best sun shading system ever. Yeah? I mean, there's probably other systems that are more effective than this one, but because it really is a new approach to kinetic systems in architecture. Yeah? Deformation by bending. Because usually, as I said before, what we usually do is we use fiber-based elements either for soft textiles, as is large stadium roofs, or for stiff elements, yeah, as is sun shading elements here in London. What we did here is we used them for, we locally adjusted the stiffness and used the stiffness to and bending to actuate this deformation. And that comes from this biomimetic approach in research. So what we do now is we investigate all kinds of plant movements together with biologists from Freiburg, all kinds of movements working with adapted local stiffness. We try to transform them to mechanical models. There are also others who are doing that. That is research that was done in Harvard. This is the opening of the lily. And that is actuated by a non-uniform elongation of the fibers. So the fibers here in the center of the petal, of the leaf, show a smaller elongation than the fibers at the edge here. And this leads to the opening of the leaf as well as to this characteristic crinkles of the lily here. And we transform them to try to understand them and to do this finite element simulation of the opening of the petals. And that is very fascinating work for me because I usually use these finite element programs to simulate high-rise buildings and bridges, and now we apply them to the simulation of the blooming of flowers. And that's, of course, a very interesting thing to do. But at the end, you want to build something. I'm an engineer at the end of the day. I don't want to do research only. I want to use that for something. And at the beginning, we did not recognize what this is good for. We found that finally during the process. So this is one of the first major buildings that we did in my office together with Renzo Piano. That's this shell in Cologne, Peak in Kloppenburg in Cologne, and nice structure. Everybody was happy. But the problem was how to put sun shading on it. Yeah? It's physically not possible to put the usual sun shading devices on this kind of complex double curved geometry because they all have this kind of straight axis of rotation or of translation. They all need this, and that is not possible to apply to any kind of complex form geometry. And this, if you do so, you end up with a nightmare here of all kinds of winches and rollers and ropes. And I don't think that this will work very well for a longer time. And this kind of systems that use only bending and not rotation or translation, they can be adapted, adjusted to any size and to any curvature of the system, and they could be used as a shading device for complex form geometries. That's where we see the field of application for that. So one of the really very, very lucky coincidences in my professional career was that just at the moment when we were working on this points, issues, we were approached by SOMA. Yeah? SOMA is a young architecture group from Vienna. They're all coming out of this Coop Himmelblau office. One of them is still working here on the EZB tower. And they won this huge competition, international competition in South Korea. And they won the competition with this rendering, with this idea of a kinetic facade. But they had, of course, no idea, no clue how to construct it, how to do it. And with that image, they came to us. And initially, we tried to apply this the system with the backbone and the soft leaf directly to this geometry of the building, but this did not really work very well because we did all the structural calculations and it was proved to be stable for the high wind loads and so on, but did not really fit geometrically to this shape of the building. So we then developed another idea which is very simple, which could not be any simpler than this. It's a strip of paper. Here we have two fixed bearings, and here we have two fingers pushing inwards. And this again leads to a buckling of the thin elements. And this kind of controlled buckling is used here for the opening of the facade. Yeah? So you can see here a simulation again. So here is a mechanical device pushing inwards, and this leads to this controlled buckling. So a small force, a small deformation actuates this complex rotational opening of the sun shading elements. Yeah? These were the first mock-ups built autumn 2011. You can see this is 40 meters high, only 8 millimeters thick, and only one stiffening rib on one side. Yeah? And here you push inwards here, and that leads to deformation. And I think even if you're not a structural engineer, you can feel how this gains stiffness from the internal stress and the deformation. And this, we have very high wind loads here at the Korean coast, but these very thin elements can take these wind loads because it's a very stiff and strong internal stress configuration there. Yeah? And also the fabrication is very simple. One mold. Here you can see the glass fibers on the roll. It's a very simple fabrication process. Yeah? And that is how it worked when we were there last year. May last year, we were there and took this images there. Yeah. You can see here the opening of the lamellas. So it's behind there is a glass facade. In front of that are the sun shading elements. In there is a complex video exhibitions. The Koreans are very keen on all this video LED stuff. Yeah? So there's a huge installation in there, and so they want to control the light, the daylight in the building. That's the building. And this is something what with a little distance now, what I found very interesting is that this is using very simple geometry, very simple materials, nothing new about it, but it still is something which is, as far as I know, which was not done before at the scale of a building. And this innovation, I think, comes from the analysis of biological role models. Okay, thank you for your attention. happy to answer any questions if there are any.
Are there scalar issues in the translation from the biological to the...
Yes, of course. So it's always a scale issue. And that's also why it's not possible to, there is a misunderstanding also of biomimetic research, to transfer directly the petal to a large building. That's also why in all these popular reports on biomimetic research, there's always this lotus effect. You probably know that, self-cleaning effect, because that is one of the very rare examples where a biological role model was directly transferred to a technical application. I would say it's more a kind of inspiration, I would say, not a direct transfer of the natural system to a technical system.
But with the fibrous materials, and you begin a new approach.
Yes.
Not a direct...
Yeah, that is an aspect that I've forgotten to mention. What is really interesting in this fibrous materials is that for me as a structural engineer, when I build a house, I take a steel girder with given properties, I buy it in a shop, and I use it with its given properties as it is. I have to deal with that. And here I can design the material itself, the fiber orientation, the fiber layout. So I just extend my design space, I would say, as an engineer. And that is a very interesting aspect on this materials.
So also here there was a highly determined, predetermined, analyzed directionality of the fibers in these fins?
Yeah, these fins are, are very simple, as I said. They are just one direction, and the content of fiber is increased from the soft edge to the stiff edge. So there are more and more fiber mats. More fiber mats on the right side than on the left side, but the orientation of the fibers is unidirectional.
Maybe you could just speculate for a moment on why we don't see more responsive and flexible architecture. I mean, just you see these incredible sort of actuators coming out of companies like Vesta that completely don't work in the same way that we do practically everything now. Soft body stuff, pneumatic actuators. But here, this is still quite a regular system. But do you think it's just European fear of weird stuff? And you do it in Korea because they want that?
Yes. That's also a very interesting point. I think that I'm sure that this building would never have been possible in Germany. Yeah. So what we did is we did all the calculations and the drawings. We handed them over to the Korean constructors, Hyundai. We heard nothing from them for nearly 1 year, and they finally came up with this mock-up. So that's a very different approach to innovation than we have in Germany in building industry. I think it's you could ask 1,000 questions from a technical perspective. You could ask 1,000 questions: fire resistance, durability, fatigue behavior. You could find 1,000 reasons not to build this something like this. Yeah. But from a technical perspective. But that's my experience that in China as well as in Korea, there's a different approach to innovation. They say we want to have something new. We know that there's a risk, but we want to have something that was not done before. And this approach to innovation is something that, I don't know what you think, Manfred, but this is something that is at the moment not there in Germany in the building industry. And that's
The actual desire
for change, for trying to do something new and take a risk also. That is something that is...
The German society is mentally one of the oldest societies. They are afraid of new things. They only want to keep what they have and they want to go back.
It's very interesting that many German engineers as well as construction companies are really on the top level of innovation and technology, but they're not working in Germany anymore. When you look at Ziele, for example, Ziele, they are doing projects all over the world, but not in Germany.
Do you build any measurement devices, any analysis once the structure is built? I mean, you said when the last it's hard to understand what's actually going on there. I'm trying to find out. I'm just thinking like the Toyota models often use gauges in there to measure the stresses in the model. And then from that, do you use that to inform computation models to kind of develop?
Yes, we did on this first model, first pavilion with this bended strips. We did a huge monitoring program, and we also we did a 3D scan to see if we achieved the right geometry. And also after we only get a building permit for 3 months, so we have to take them down after 3 months, and we have seen how this strips that were initially straight were then bended, and what this means to the internal stress. Yeah. We do a monitoring program on the pavilions, but here again it's a cultural difference. The Koreans say if they decide to do it, they do it, but they don't want any Europeans anymore to be involved. Yeah. They want to keep the expertise and the experience. They want to keep them that. And don't share it, which is a pity, of course, for us. Not at all. So we did a lot. We did a lot of calculations and drawings, and we handed them over, and that's it.
Also, no influence on quality control.
No.
Is that why there's no actual sort of video from this distance of the entire facade moving, which I find quite strange. Like one close-up shot of a few panels moving. We were there as tourists, I would say. Huh? So we were visiting the. So I was. It seems like quite a dramatic structure that probably cost a lot of money. I'm just wondering why there isn't a nice HD camera put there.
When we were there, when we were there during the expo, it was only used during nighttime, because during daytime they wanted to have no daylight in the building, and we had no professional equipment with us to do a video during nighttime. They just did that for us as visitors.
Question. Do you see a chance in developing the bending actuation process by using special materials that are fine materials?
Of course, yeah.
I was just reminded by the lily pad.
Yes.
It seems to be ideal to combine these effects together, the energy from the material directly, without using these energy.
Yes, we try to. We have now in prolongation of our research project on this Strelitzia, on this Bird of Paradise project, and we try now to look on self-actuating systems, the different ideas. You could use different types of fibers with different thermal elongation, and then you could increase the temperature, and by that you could bend the backbone. So we're working on that. This is, of course, this is a question which is asked very often. Yeah. But here you have electric devices here on each lamella, but you have to remember that the energy of the device is stored as a kind of stored as elastic energy in the elements. And when you release them, you can recover or regain a certain percentage of that energy again.
One thing I want to ask always interested in is the sort of methodology of the collaborative aspect. You made 2 points during the presentation. You referred to it. You had your diagram up there. You said this is the conventional working process, and then you have your underneath the diagram showing what I think you referred to as the parametric or the shared model. So that was one point. The other point where you spoke about this was when you showed the team photograph on summer pavilions. And you basically described that situation by referring them practically to the photograph and the roles of the people, so they have to define their own input. I think you also said it breaks down the conventional role model for how you do things. And what is your experience of this in terms of, say, research and theory on one hand, and then practice on another? Because you have then also done certain projects where you begin to use some of these.
I think that is a very important aspect, because in 99 or 95% of all real life design processes, it's up there. So there's a well-defined scope of design for each one involved, based on a fee regulation, and everyone is first looking at his own box, what he has to do, what he has to get from the architect or from the client, what he has to provide to the next one who's coming after him. So this is a very limited view. We are forced to do so because we get a fee, and the fee is limited, and we cannot do everything. But what is interesting here, and that was really something that was very interesting for not only for the research projects, but also for Shenzhen Airport, for example. We need a 3D model for the geometry, but who is doing that? So you sit together at the table, and you're discussing, the beginning of the project, you're discussing who is doing what. And you also have to ask yourself as an engineer, what can I do? What do I want to do? How do I want to be involved in the process? And there's a very different approach to start the design process, and to know this is my scope of work. I have to get this. I have to provide this. And I think that this is also a very important aspect, bearing a potential for innovation that is not recognized, that you redefine your own role in the whole process at the beginning, and discuss that with your partners.
And does it include participants on that on the left side of the diagram, or also on the right side when you're speaking about fabrication and construction?
Yeah, I could show other projects where we were working on the side of the constructor, but were responsible for the 3D model development. This also involves the constructor, not in this specific example of the Shenzhen Airport, because that's the same as for the project in Korea. At a certain stage, you hand over your documents, and that's it. But in other projects, the constructor is also involved, of course.
I think also this is a very important question. When you work in China, you have a completely different situation with the cooperation with the contractor. There is no bidding phase. In China, things are going a certain way. No one really understands which way they are going. So, to my experience, there are always two questions. One is the question of money. Who is paying the extra work that is necessary to work on the parametric model? And the other is the question of responsibility. Here in the Western countries, there is a very decisive, normally for project, there is a very decisive step when you hand over the documents to the contractor. You also hand over the responsibility for the quality, and the responsibility for cost, and the responsibility for maintenance and for everything. So it's in a legal way. This is very difficult if you hand over a complex data set. Who
That's why very often in the international context we have this design and build process, that there's some kind of idea of the architect, and then the contractor is hired to do the whole design process, including structural engineering works. Because then all the responsibility is on the side of the contractor.
Contraction.
Yeah.
Well, thank you very much.